In this short video, we will be looking at the formation of the water molecule, the carbon dioxide molecule, and the carbon tetrachloride molecule. We will look at the Lewis structures of these molecules, the electronegativity differences between the atoms in the molecules, and also the intramolecular bonds within the molecule. Those are the covalent bonds. We will then look at the molecular shapes of each of these molecules, and we will also see whether the molecules as a whole are polar or non-polar molecules. Before I continue with each of those three examples, I would like you to please take note of the following. These are definitions that you need to know, these 5 definitions. I dealt with these in the video part 1, chemical bonds part 1. I also want you to take note of electronegativity on the periodic table and where it is located for each element, because that is quite important for this lesson. And we are going to use the periodic table to see how many valence electrons each element has. The number of valence electrons corresponds with the group number. You will be using the electronegativities as well to determine how polar covalent the bonds are. So for the water molecule, we're first going to look at the Aufbau diagram for oxygen. Oxygen is in group 6. It has 8 electrons. I would like you to keep a periodic table handy. So if you don't have one with you, go and fetch one, pause the video so long. So if you look on your periodic table, oxygen is in group 6. So oxygen has 6 valence electrons. If we fill the Aufbau diagram, we would start with putting 2 electrons in the 1s orbital, then 2 electrons in the 2s orbital, and then we go 1, 1, 1, and then we start again with the 8th electron. So there are 2, 4, 6, 7, 8 electrons. 8 electrons in an oxygen atom. Oxygen is in group 6, so it has 6 valence electrons. Here they are. There are 2 lone pairs, and there are 2 unpaired electrons. The unpaired electrons are available for bonding. So oxygen makes 2 bonds. The electronegativity difference between oxygen and hydrogen, here's oxygen's electronegativity, and this is hydrogen's electronegativity, is 1,4. Because of this electronegativity difference, the bonds between oxygen and hydrogen are polar covalent. That means one of those elements attracts the shared electron pair more. And that would be oxygen, because oxygen has the greater electronegativity. Oxygen has a higher electronegativity, therefore pulls the shared electrons to itself. To do the Lewis structure for water, we start with the element that makes the most bonds. Oxygen makes 2 bonds, hydrogen makes 1 bond. So I'm going to put the 6 valence electrons around the oxygen atom. You just go round and round. So there we go. There's the 6 valence electrons around the oxygen atom, 2 lone pairs, and 2 electrons available for bonding. So the hydrogen, which is in group 1, has only got 1 electron. So each of the 2 hydrogens bond to the unpaired electrons. That is the Lewis structure for the water molecule. If you want to draw the Cooper structure, for each bonding pair, you just do a line. So there's the Cooper structure for the water molecule. And then some of your teachers might put the lone pairs on. Just do what your teacher does. On the top right-hand side of the page, I have another drawing of the water molecule to indicate the single covalent bonds between the oxygen and the hydrogen. There's one, and there's the other one. The 2 lone pairs, there they are, they push the 2 bonding pairs away, resulting in an asymmetrical molecule. That means your molecule is not symmetrical. An asymmetrical molecule. This is important. The lone pairs push the bonding pairs away. Here's the bonding pair, there's the other bonding pair. The molecule is more negative on the oxygen side, up here where the oxygen side is. The yellow is the oxygen, the two black ones are the hydrogens, and it will be more positive on the hydrogen side. So this molecule has a positive side and a negative side. The molecule is therefore polar. We call it a polar molecule or a dipole molecule. The shape of the molecule is angular. In certain textbook study guides or on the internet, they might say bent, but we mainly call it angular. And the bond angle is 104.5 degrees. Important things here. The electronegativity difference is fairly large, 1,4. So the shared electrons are pulled closer to the more electronegative atom, which is the oxygen. So these are polar covalent bonds inside the molecule. There are your two polar covalent bonds. There are two lone pairs which push these bonding pairs away. This results in an asymmetrical molecule. So the molecule becomes more negative here where the oxygen is and more positive where the hydrogens are. So the molecule is therefore polar, and we call it a dipole molecule. The next molecule that we're going to look at is carbon dioxide. The Aufbau diagram for carbon is on the left-hand side. For oxygen, it's on the right-hand side. Carbon has got 6 electrons. It is in group 4. So it has 4 valence electrons. Here they are. Valence electrons are electrons in the highest energy level. We call these core electrons, the ones closest to the nucleus, core electrons, and these are the valence electrons. And the same on this side. Here, 2 core electrons, closest to the nucleus. Carbon is in group 4, so it has 4 valence electrons, but because the 2s and the 2p energy the sublevels are so close in energy, this electron would leave the s orbital and go to an empty orbital so that they could be more spaced out. In the oxygen atom, there are 8 electrons, of which 6 are valence electrons, 6 electrons in the highest energy level, the 2 lone pairs and the 2 available for bonding, as we saw in the water molecule. The electronegativity difference is 3,5 minus 2,5. The oxygen electronegativity from your periodic table minus the carbon's electronegativity. A difference of 1 is fairly significant. This will result in polar covalent bonds between the carbon and the oxygen. We're going to look at the Lewis structure now for carbon dioxide. I'm going to start with carbon because carbon can make 4 bonds. Oxygen only makes 2 bonds. So we start with the element that makes the most bonds. There's the Lewis structure for carbon. So I'm going to do an oxygen now with the 6 valence electrons because it is in group 6. And you can also see from the Aufbau diagram why it has 6 valence electrons. So each oxygen can make 2 bonds. Carbon wants to make 4 bonds. So I need 2 oxygens. So we can have overlapping of orbitals there, 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 and there. So the one carbon atom is going to have 2 bonds with each oxygen. So here's the Lewis structure for carbon dioxide. I'm going to put the 2 lone pairs in. And then the bonding pairs we put between the atoms. So there's the 2 oxygens bonding electrons with the 2 carbon. And then the carbon's 2 bonding electrons that bond to the next oxygen. And the lone pairs go in. This is the Lewis structure for carbon dioxide. You can see there are no lone pairs on the central atom, which is carbon. That is very, very important to note. Always check to see whether there are lone pairs on your central atom. Carbon makes 4 bonds, oxygen makes 2, so carbon is my central atom. I have 2 double covalent bonds in this molecule. A double covalent bond here. Let me get my pointer. We have a double covalent bond there and a double covalent bond there. The Cooper structure indicates it here. So now when I want to look at the polarity, I've looked at the polarity of the bonds. They are polar covalent because oxygen has a much greater electronegativity than carbon. So the pull of the shared electrons, the oxygen pulls them more strongly. I'm just going to do that in another color. So the oxygen pulls the electron pair more strongly, so the shared electron pair. So the oxygens are more negative, the carbon is more positive. So if we look at the diagram on the top right-hand side, the oxygens are the blue circles, the carbon is the yellow. Here's your double polar covalent bond, and there's the other double polar covalent bond. We have a negative on the outsides and a positive on the inside. Because there are no lone pairs on the central carbon atom, the molecule is symmetrical. The molecule is more negative on the oxygen atoms on the outsides and more positive on the central carbon atom. There is no positive or negative side. The molecules are therefore non-polar, but the intramolecular bonds, the covalent bonds, are polar covalent. Listen carefully, the molecule is non-polar because it does not have a positive and a negative side, but the bonds inside the molecule, the intramolecular bonds, are polar covalent. The shape is linear, it's in a straight line, and the bond angle is therefore 180 degrees. All linear molecules have a bond angle of 180 degrees. The last molecule I'm going to look at is carbon tetrachloride. The Aufbau diagram for the carbon atom, it is in group 4, so it has 4 valence electrons. Each carbon atom has 4 valence electrons. This electron can be on its own. It would prefer to be on its own, so we'll move it to the empty orbital. Chlorine is in group 7. It has 17 electrons in total. So if you just want to study the Aufbau diagram in your own time, the 7 valence electrons are the electrons in the highest energy level. So there are 3 lone pairs and 1 unpaired electron. So chlorine makes 1 bond, carbon makes 4 bonds because it's got 4 unpaired electrons. The Lewis diagram for carbon tetrachloride, I'll do that now, but we're first going to look at the electronegativity difference. This is chlorine's electronegativity. Now that's quite untidy. I'll do it again. Chlorine's electronegativity is 3 and carbon's is 2,5. So that's a difference of 0,5. So it's not as polar covalent as the other 2 examples we've looked at. It is slightly polar covalent. So the chlorine has the greater electronegativity, so it's going to pull the shared electron pair towards it. So I'm going to start with the element that makes the most bonds. And which element is that? It would be the carbon. Carbon makes the most bonds. Carbon has 4 valence electrons. So you put 1 at the top, 1 on the side, 1 at the bottom, 1 on the side. Each chlorine has got 7 valence electrons with 3 lone pairs and 1 unpaired electron. So I'm going to put a chlorine to the right, a chlorine underneath. My Cls are not that neat, but you know they're chlorines, and a chlorine on the left. So I've got the bonding electron for each chlorine, but each chlorine has got 3 lone pairs, so I still need to put those in. I apologize for the untidy Cls. And then the 3 lone pairs on the last one. So the chlorine's valence electrons are crosses, the carbon's valence electrons are dots. This is the Lewis diagram for carbon tetrachloride, and the Cooper structure would just be a single line to show the single covalent bonds between carbon and each chlorine. Right. So again, the electronegativity difference between chlorine and carbon is 0.5. So these covalent bonds here are slightly polar, with the electrons being pulled slightly more towards the chlorine, the shared electrons. So we're going to have negative, 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 negative on the outside and a positive on the inside. So this molecule, again, there are no lone pairs on the central atom, the carbon. So there's no pushing away of lone pairs, pushing away the shared electron pairs. So our molecule, we call it tetrahedral. So we have a three-dimensional shape. Look at the top right-hand side, a three-dimensional shape with a carbon in the center and the 4 chlorines evenly spaced, three-dimensionally, evenly spaced around it. The bond angle in this molecule is 109.5. So this angle between the 2 chlorines is 109.5. All of the bond angles are 109.5 degrees. So try to imagine this three-dimensionally with all the angles 109.5 degrees. There are no lone pairs on the carbon atom, therefore the molecule is symmetrical. The molecule is more negative on the chlorine atoms on the outside and more positive on the central carbon atom. So there's no positive and negative side. The molecule is therefore non-polar, but the intramolecular bonds are slightly polar covalent. This shape is called tetrahedral and the bond angle is 109.5. Now there are some more tetrahedral molecules, and they all involve carbon and another element that only makes one bond. So carbon tetrabromide, we've looked at carbon tetrachloride, so carbon tetrabromide, carbon tetrafluoride, carbon tetraiodide, and methane. These are all tetrahedral, non-polar molecules, because they're symmetrical, with 4 polar covalent single bonds. Carbon, which is in group 4, makes 4 bonds. Hydrogen is in group 1. Fluorine, chlorine, bromine, iodine are all in group 7. They are halogens. They also all make 1 bond. So all these molecules will be C and then something else, of which we will have 4. There are no lone pairs on the central carbon atom that push the bonding pairs away, and these molecules are therefore symmetrical.